Well, how are you doing? Okay, this is going to be a quick video on the nonsense that they call spherical triangles. There is no such thing. I'm going to show you here how there's no such thing and how there can't be such a thing as a spherical triangle. And I'm not going to use, yes, I will use the usual and most obvious way of debunking it, but there is a secondary way. Okay, right, so let's start here with the definition of, sorry, right, angle from Cambridge Dictionary. The space between two lines of surfaces at the point at which they touch each other are measured in degrees. The interior angles of a square are right angles or angles of 90 degrees. The both settled into the mud at 35 degrees angle, at an angle of 35 degrees. The corner of a building table or anything with straight lines. Right, more examples. The wall was leaning at an angle of 10 degrees, blah, blah, blah. A right angle is an angle of 90 degrees. Um, a position from which something is looked at, that's more perspective. A way of considering blah, 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 blah. But the basic of it is, right, is that you're talking about two straight lines meeting at a vertex. That's what it is, okay? Um, if you want to talk about an angled line, it's not horizontal or vertical, but sloping in one direction. But the point is straight lines. You must use straight lines. So, what is a line in math definition? Right? In geometry, a line is a straight one dimensional figure that does not have a thickness and extends endlessly in both directions. Okay, so in geometry, a line is defined as something that's straight, one-dimensional, and does not have thickness, and it extends endlessly in both directions. Sorry, that was a bit dry. Angle between two lines, right? Right. Two straight lines, right, meeting at a vertex. That's an angle, right? So straight lines. This is the most important part. You need straight lines to measure an angle, right? Definition: the degree of curvature is defined as the central angle to the ends of an agreed length of either an arc or a chord. Right. This is what is a curved angle. Right. Various lengths are commonly used in different areas of practice. This angle is also the change in forward direction as that portion of the curve is travelled. Right. So this is what we're talking about as a curved angle. So what's a curved angle is this. So you have two radii, right, lines coming from a central point, meeting at the circumference, right, or surface of the sphere or circle, and you have a chord between them, and this allows you to define how much arc will be there, right? So it's the radius and the angle of the angle between the two radii allows you to define, because you know what the size of this circle or sphere is, allows you to define the arc, right? Go. Can a triangle have more than 180 degrees, right? The three interior angles of a triangle will always have a sum of 180 degrees. A triangle cannot have an individual angle measure of 180 degrees, because then the other two angles would not exist. 180 plus 0 plus 0. Right? It doesn't work. The three angles of a triangle need to combine to 180 degrees. Everyone knows that, right? But they want to claim a spherical triangle can have more than 180 degrees or whatever, right? They want to claim that there's other triangles. No, there is not, right? Those things don't exist. But it's you can make yourself believe they do if you cheat. That's about the size of it, and I show now. So equilateral ideal triangle in flat space: A equals B equals C equals 60 degrees. A plus B plus C equals 180 degrees. Equilateral ideal triangle on the sphere: A equals B equals C equals 90 degrees. A plus B plus C equals 270 degrees. So how are they getting 270 degrees here? Right, this is the thing, right? Let's go to this, right? So, right, they're trying to say that's a 90, that's a 90, and that's a 90. It's not, can't be a 90. These two lines are curved. These two lines are curved. These two lines are curved. So you can't get an angle between two curved lines. Can't be done. But they do have 390, but this is created with 390 degrees. Okay? It's created from a central point. When you put an XYZ coordinate system into the center of a sphere, This here is an angle of 90 degrees, this is an angle of 90 degrees, and this is an angle of 90 degrees. So they do have three 90 degree angles, but it's from a central point. It's not from here. These 3 points here, right, are points on the sphere that they create via these angles, right, via these lines from the center point, right, and they then, because they know the radii, they just join up, right, the arc from point to point, but they are still chords, right, 3 chords and 3 angles from this point, and because they know the radius, they can join up the arc, and that's what they do. So they're not; these are not measurements. I'll show again. These are not 90-degree angles. Nobody is on the surface of a sphere measuring this nonsense. You can't do this. It's rubbish, right? So anyone who's claiming they're measuring this on the surface, anyone who's claiming they're on a sphere, Earth, and are measuring these things on the surface of the sphere are liars. You can't. You must pre-assume a radius, and you must bring everything from the center. You can't do this. You can't measure angles between curved lines. You can't do that. It's not possible. Angles require straight lines at all times. So these 390-degree boxes they're trying to show here, they're not on the surface. They're at the center. They're at the center point. That's where they're from, not on the surface, right? You can't. So when people are trying to claim these false surveyors and that they're claiming that they're measuring spherical excess, this absolute nonsense. And I've told people this for years and years and years, and they won't listen. They are not measuring spherical excess. It's a mathematical thing. It's maths that they do after they have calculated, right, the 3 points they want on the surface of the sphere. Because that's all they're doing. They're just calculating 3 points from a center point using a radius that they don't have because it was never measured, right? Well, the only evidence of a measurement for their radius is a back calculation of flat Earth elevation angles to Polaris, as I show in another video, how the whole thing happens. Whole 40 made a video going through the whole thing and how it happens. That's the only claim to a radius they have. A flat Earth is the only claim that they have to a radius for their globe. So all they're doing is they're taking this radius that they know they have, and they're taking 3 lines from a center point. Let's just say in simplistic form, like here, by using very simplistic XYZ 90-degree angles from a center point, and then they have chords running here, here, and here, and they're calculating what this arc would be for each 3. And they then can go back and put this nonsense here, right, and make a diagram like this and say, see, a triangle on a sphere. How can a triangle have 3 90-degree angles within it? It can't have 3. It can't have 2 90-degree angles, because then it's 2 verticals and a horizontal. It can't have 2. It can have 1 90-degree angle and a 60 and a 30, that kind of thing. But it can't have 3 90-degree angles, and it can't have 2 90-degree angles. But you can, from a central point, have 3 90-degree angles. You can make a load of different spherical triangles on the surface of this sphere from a central point using Cartesian a Cartesian system, which is a plane through the center. You can do that in all directions here, above, out, this way, this to the left, to the right, below. You can make a load of what they're calling spherical triangles, but they're not triangles. They're just 3 curved lines meeting. It's not a triangle. There's no angles. You can't measure an angle between any of these points. There's no measurement you can make. It can't be done. It's impossible to measure spherical triangles. It's impossible to measure an angle using curved lines. Can't be done. And just to show, this is from Rob Durham. Hopefully you can hear this, okay? And this is when he was making a joke of the globe with angles and circles of equal altitude. I'll just leave him play this here. This is what CAD has to say about angles using a curved line.
Is because the Earth is flat. Okay, to briefly touch on what the guys over at Flat Earth Debate have been saying, we're going to use the exact same examples of the GP positions here. I'm going to look at it from an orthographic view. Okay, if we're standing here on the Earth, this is the angle to the celestial body. Let's take a line from our position representing the horizon. The angle formed here is definitely not 90 degrees. And even at the position where it meets the Earth, you can't have a 90-degree angle to a curved surface. And AutoCAD will actually verify this, because if I choose the angular dimension command and I pick this line and this line, it will give me an angle between them. If I try to pick this line and this arc, it says here, object selected is not a line. So it will just not give me an angle. And why would it? How could it? The angle will be different at every single point on that arc.
Thank you, Rob. See, can't be done. And just to just to prove it further, here is Geogebra. Right, where are we? Angle, right? So I want to get the angle between A, D, and B, right? So I'm going to go from A to D to B. Now, if I can get an angle using a curved surface, then there should be no reason for what Geogebra does to reference anything but this curved line here. So I'm using two straight lines and a curved line. So if it's possible to get an angle using a curved line and off of using a curved line and off a curved surface, then this should work. So A, B, D, B, right? Sorry, I'm gonna have to change that to 180, right? So there's something wrong here, right? Because if I just get rid of this, sorry, right, there's my 91.86 degree angle. If I move in, as you can see here, this line is not matching up with this green line. So one second now. So going to settings very briefly, and I'm going to go to style. I'm going to bring up this and color, bring that up and make it purple. Right, so as you can see, it's not referencing this green line. That's what it's not doing. What it is referencing is a segment between here and here. So that's what it's referencing. It won't reference this curved surface. It won't do that because you can't get an angle off a curved surface. So if I have two curved lines, how am I supposed to measure an angle between two curved lines when I can't even measure an angle with one curved line and one straight line? It can't be done. You can't do this. It's not possible. And just to further show, the 3D calculator, there's 3D calculator, right? Right? Here you have, in between here, this is the XYZ Cartesian system that they've placed in the, it's placed in the center of this sphere here. In here is where the angles are coming from. These are the 3 90-degree angles. 1, 2, 3. That's where the angles are coming from. Not on the surface of any sphere. It doesn't work. You can't do that. It's not possible. So if you can't get an angle using a curved line, how can you measure a spherical triangle on a surface, on a curved surface? You can't. There's no such thing as spherical triangles. There's 3 curved lines meeting, that are meeting together, and those 3 points that create those 3 curved lines were created from 3 actual real angles from a central point. Right? That's what they're actually doing. There's no such thing as measurement of a triangle with curved lines on the surface of a spherical anything. That's nonsense. It's purely mathematics coming from a central point using the XYZ Cartesian system. That's all it ever was. It's all it ever will be. No one's on the surface of anything measuring angles with curved lines, right? Just there you go. Can't be done, right? You can't measure an angle of a curved surface. So you can't measure curved triangles, can't measure elevation angles of a curved surface, can't do any of that. That's not what you can do off a curved surface. I don't know what you can do, but you definitely can't do that. Thanks for watching.